Good afternoon, everyone. Welcome to today's WebEx. I am Elizabeth Berry, Marketing Communication Manager here at Lincoln Electric. Thank you for attending. Our topic today is reducing surface silicates. Before we begin, I'd like to cover a couple housekeeping items. All attendees are on mute today. So if you are having any issues or problems, please submit through the chat functionality and we'll try to assist you any way possible. But throughout the web session, if you have any questions or would like to have our speakers answer any questions at the end, we would ask you to submit those through the chat or the Q&A functionality. So the little air bubble that appears in WebEx is how you would do that. Our speaker today is Tim Hurley. He has many years of industry experience and has been with Lincoln Electric since 1986. Welcome, Tim.
Thanks, Elizabeth.
Did you want to introduce Badri as part of your session today?
Sure. With me today, Dr. Badri. He is our Director of Global Consumable Strategy. Badri has been with the company for over 20 years. He's a PhD in Material Science and Engineering and is an adjunct faculty position at Case Western Reserve University in the material science area. Badri's responsibilities are managing our global consumable product portfolio for Lincoln Electric and also the technical development and supporting new product development and our overall global strategy. I didn't introduce myself maybe as much as I could have. My primary responsibilities for Lincoln as Director of our Transportation Industry segment are trying to lead the development of both new product and solutions, so industry-leading solutions to address the challenges of our transportation industry customers. Badri, you there? You say hello just to make sure your audio is working properly.
Hello, everyone, and glad to be here this afternoon talking to you about what we think is going to be an interesting subject for you all.
Thanks, Badri.
Just, Tim, on a side note, I think you're having a little bit of backfeed, so I know there's been some comments here that you're kind of cutting out a little bit.
Okay. I will work on my audio connection here and speak slowly and succinctly. So we appreciate everyone's. Thank you. We appreciate everyone's time in our webinar today. This is a repeat of something that we did weeks ago, and the importance of this. Well, number one, we appreciate the time as people are home, staying safe, that they are tuning in for this period of time to listen to some of the innovation that Lincoln is bringing to the marketplace. And what we hope to cover today to show some value to you is we'd like to talk a little bit about why there's an increased focus or a broad global focus really on eliminating silicates on gas metal arc welding deposits. Talk about the mechanisms of silicate formation, some of the variables that affect that, so things that we have within our control in the welding industry to reduce those that silicate formation, how we can optimize those controls to give us the best possible solutions. And then Badri is going to cover some of the new filler metal and process developments that Lincoln Electric has been pursuing to further improve the current state of silicate for many MIG welding applications. We'll talk a little bit about the future development as well. We see this increased focus, I believe, is in any vehicle applications and even outside of vehicle applications, but even in farm implements, transportation type of anything that moves, really, we're looking for improved vehicle performance, improved fuel efficiency, and so lighter weighting of vehicles is important. We're using higher strength materials, thinner cross sections, so corrosion life becomes an issue. Dealing with that corrosion life is a problem with silicates because they are non-conductive. They don't wash and clean very well, and expensive material removal such as media blasting is not typically done. It is in some industries, but is not typically done in high volume production. The silicates themselves do not paint very well, so paint adhesion is an issue. You look at a picture here of just a simple MIG weld, typical silicates on the surface, but then after electrostatic painting, you can see that there are voids where that coverage does not adhere. This is because of the electrostatic method does not allow for good paint adhesion. Those become premature locations for rust, and even the image themselves of the welds with this reddish brown color to them actually appears to the common eye as a rust spot, and so that becomes a warranty issue or customer problems for any of the OEMs that produce products. So how silicon islands are formed, really, it's a silicon manganese oxide. They're all, they're known commonly as silicon islands. These, the purpose for having silicon and manganese in the weld wire and the steel itself is it does act as a deoxidizer, so it scavenges oxygen and floats it to the surface, so we don't have that in our weld metal. These elements also improve puddle fluidity, so you get better bead geometry, angles, fatigue life from that. They help to reduce spatter, and in the case of manganese more silicon, it improves the strength of the steel. So the silicate formation itself is really done as you look at the arc itself. The exposure of molten metal at certain temperature ranges is where the silicon and manganese adhere to and attach to the oxygen itself. The shielding gas or oxygen in the atmosphere can be sources for this combination. What we see is in that arc itself, as the droplets are being transferred from the wire to the base material, that area is really where the exposure takes place most commonly. It's also in the weld pool itself. So the electrode, when it's heated, is this mechanism to take place. The droplets during the arc transfer and part of the weld pool are all going to be locations and times, depending on the temperature range of the weld metal, where this silicon oxide can be formed. Borrowing from some research that was done by a gentleman named Richard Darien from the Colorado School of Mines, these are some pictures that of the silicon being formed actually on the ball as the wire is being fed into the arc. You see that red area is the silicate itself. As the droplet nears detachment, you can see there's actually more silicate on the surface of that molten ball about to be detached. And then as it transfers to the molten puddle, we can then see the red zone in the molten puddle where the silicate that was on the droplet is now part of the weld pool. That weld puddle or molten pool is being exposed to the shielding gas is also another source to attach itself to the oxygen. So the primary contributors, there are really four components that are the primary contributors to the silicate formation: shielding gas and the percentage of either oxygen or CO2. We're going to look at the welding process itself. So what parameters do we run? What kind of modes can we use? What can we do from a torch angle standpoint? The filler metal chemistry is obviously a contributor. That's part of the chemistry of the ultimate weld deposit, and the base material then mixing with that filler metal is the fourth component. Now, there within the welding process itself, we really have control over three of these four, so we're going to focus on those three, and then we'll talk a little bit more about the changing base metal chemistry. So this again, from master's thesis from Colorado School of Mines, what we see is that within the many shielding gases that were tested, 90%, 10% CO2 really gives us the best performance overall. The traditional CO2s, 25 CO2s, those kind of gas mixtures, what you may think it would be an even better improvement, which would be a 5% oxygen, actually has higher silicate formation rate when compared to the 90-10. So there are some lower rate gases here that you can see at the bottom, but most of those really are helium-based, non-traditional, pure argon, non-traditional steel type of gas mixtures. So what we see is really that the 90-10 argon CO2 is preferred even over a 95-5 for giving us the lowest rate of silicate formation. Now, when it comes to welding parameters themselves, some of the key elements that we've identified as being the greatest contributors or things that we have within our control, travel speed is one of those factors. Higher travel speed actually acts as a faster solidification, and with that faster solidification, you have less of that molten puddle exposed to the atmosphere or to the shielding gas, and so you have lower silicate production. You see here pictures of the same wire being used in two different applications on the same base material. The welds on the left are what we would classify as more of a heavy fabrication weld, so slower travel speed. and higher voltage, broader arc, a bigger weld on heavier material. But when you move to the right and you see the automotive welds, those are single pass, higher speed, and significant reduction in the silicate formation when we move from that slower to the higher speed. One of the things that we have noticed, though, that we have kind of an asterisk on this is up to about 45 or 50 inches per minute, that travel speed correlation, or the inverse correlation, I guess, to silicate formation proves to be effective. Meters per minute. We haven't done a tremendous amount of testing at the very high speed range, but the faster travel speed equals lower silicate production is really seems to be more up to a certain limit, I guess, is what we would classify that. The other thing that's different between these two welds, though, is voltage. One of the things that we're going to talk about, voltage is a very significant factor in a couple of different ways, and so we're going to look at that on why voltage is such a significant factor in this. So if you look at two welds being made in this application, maybe this one's made at 24 volts, you have a longer arc length, broader arc as it intersects the base material. You look at a shorter arc length at 22 volts, you have less droplet exposure. If you look at the time and the distance over which the droplet transfers through that shielding gas on, and you also intersect the base material in a narrower fashion. So what that leads to is the lower voltage and shorter arc length gives us less droplet exposure. So across that arc, we have lower droplet exposure to the shielding gas, so there's less silicate formation. The other thing that the lower voltage operation provides is that as we intersect that base material in a narrower, we can actually run a faster weld. We don't have to slow down and fill in as much base material or as much filler metal to fill that slot. So the lower voltage and shorter arc length actually contribute to higher travel speed. So that is a bonus on top of the less droplet exposure, is that the ability to run faster, again, gains some advantage in reducing the silicate formation. One of the other elements, though, that's very important in this low voltage operation is the filler metal itself. So Lincoln makes an engineered, what we would classify as an engineered MIG wire under the Super Arc or Supra MIG names. We manufacture under various names in our locations around the world. What we see here is actually a chart of a test that we would do called breakover voltage. What breakover voltage means is the wire is run at a fixed wire speed, and then we reduce voltage. As we reduce the voltage, we measure the shorting events. So the more shorting events that occur, the more spatter that is generated. So as shorting events go up and voltage goes down, shorting events go up. So each wire is characterized. This green graph may represent some particular brand of wire that breakover voltage, or the point at which shorting events occur, may be 28 or 28.2 volts. Blue wire is a different wire, different brand, and its characteristic breakover voltage may be somewhere between 27 and 28 volts. The Lincoln wire in red operates somewhere below 27 volts. So just the wire itself and how it can maintain a low voltage operation and still maintain low spatter is part of how that wire is manufactured, the surface condition, the alloy content, and so that wire is a contributing factor in the ability to run voltage, which is very desirable for reducing silicate formation. Again, shorter arc length, lower voltage equals less droplet exposure. So when we look at the traditional wires, what filler metal would we recommend? You look at a 70S3 and a 70S6 are the most common North American grades of wire that we would use. You see there's a difference in both manganese and silicon levels between those two wires. The one thing that we should mention that comes in as we start talking about re-engineering and designing some wires is there are other elements that can act as deoxidizers. Things like titanium, zirconium, aluminum can all be added as additional micro-alloying elements that will can affect the way the silicate formation takes place. So if we looked at this, this is a test that we did really using those heavy fab type of parameters. So the pictures you saw before, the bigger welds, wider welds, slower travel speed. We're running at a 90-10 gas mixture, so an optimized gas mixture. And we look at the 70S3 wire, which has lower silicon levels. Both L50 and L58 on this graph are 70S3 wires. We compare that to a 70S, which has a higher silicon level. That would be our L56 product. And really, under the heavy fab type of welding conditions, we don't see a tremendous difference between the 70S3 or the 70S wire. The variation that we see makes them within the same grouping. What we can do though is take a 70S6 micro. We add some different deoxidizers or surface tension modifier, small amounts of elements, and we really see a L59. Even though it's a 70S6 wire and would be higher in silicon, we can get significantly better performance out of that wire. So that becomes our wire of choice for reducing silicate formation. Contact tip torch optimization is sort of that fine tuning of the process that we to see what we can do to, once we've made the best selection on wire and output, what can we do to further improve operation. We take L59, which is the preferred wire that we talked about. We use Rapid X form, our Rapid X waveform, very low voltage, so we run a shorter arc length and a relatively high travel speed on these weld examples for 40 inches per minute. We see actually pretty good performance here as you're looking at. So there are some surface silicates, but overall it would be a good performance on this type of base material. But by manipulating and optimizing this contact tip to work distance and torch angle, we really find that we can get significant improvements. So the fine tuning part of this, optimizing everything that we can from a wire and gas selection and process selection, and then further improving our performance with torch angle, contact tip to work distance, and some of the finer tuning elements, gives us a difference from here to here with really no change whatsoever in our welding parameters. Really just using what we have learned on this optimization of the torch positioning. And we've done this with great success in other parts of the world. Actually, in Europe, these are two examples from our European over the course of the last few years, where using the right mode, wire, and process optimization results in some very good welds on actual parts. You see the Super MIG wire is something, again, it's a European branded product that Lincoln, we're using a Rapid Arc or Rapid X process and high travel speeds with these low voltage operation. We really are able to demonstrate the capabilities of the full package. With that, I'd like to hand over to Badri and have him discuss a little bit of how base material affects this operation and what we can do from a filler standpoint.
Thanks a lot, Tim. So I'll take you through the rest of this presentation before handing it off back to Tim to end the talk. What I like to talk is about a different variable which some of you may not realize in a typical automotive type application, that it becomes this critical in your choice of procedures, base material, procedures, filler metal, as well as what kind of manipulation you can do from a welding process standpoint. Tim talked about shielding gases, contact tip to work distances, the necessity for specific alloyed wire with specific surface engineering to enable you to weld at low voltages, short arc lengths, minimize contamination, try to get as low a silicate islands as possible. So when we started this work to understand the different variables, we started off with a standard, typical automotive grade A656 grade 80 type steel. And you can see the alloy content, the manganese and the silicon are on the higher side when you compare it to an SPH 440, which was the preferred choice for base material for some specific customers of ours. But we did all our work on what was available in North America, a standard automotive grade at 1.6 manganese and 0.2 silicon. And we later on started comparing it to another SPH 440, the base material, which was much lower in manganese and silicon. And the results I'll show you will show you how things dramatically change when you go from one base material to another. So the prototype wire we developed to look at minimizing silicate islands was a very lean wire with lower manganese and lower silicon in the wire. And when we evaluated it on an ASTM 656 grade 80, which had about 1.6 manganese and 0.2 silicon, it performed really well. And we thought we had something with this prototype wire, and we thought that this gave us the best opportunity to minimize silicate islands with all the other levers which we could turn to optimize this process. But then when we started taking this particular prototype wire and put it on an SPH 440 material, which is also automotive grade, but has much lower alloying elements, so manganese of 1.1 and silicon of 0.18, it didn't perform that well. In fact, it was terrible. So this got us to thinking about the base material, and we knew from other work we had done that base materials do matter, but we just didn't expect it to have this big an effect in this type of an application. So we took that particular SPH 440, which was preferred by our customer, and we had to adapt our designs in order for the filler metal to behave better on this particular base material. And so we looked at two things. We looked at silicon additions, obviously, because silicate content should depend on the amount of silicon in the wire. And we also looked at different microalloying elements in the wire to see what effect that does to the formation of silicate islands. So, and in conjunction with modifying the welding process, we were trying to figure out if we could minimize spatter and modify the puddle fluidity to also give an optimal solution on this particular base material. So the electrode design, we looked at a small DOE where we obviously looked at the critical deoxidizers which are added to these types of wires, which is manganese and silicon. But we also looked at several microalloying additions to the design, which would affect both the deoxidation process as well as the surface activity of the silicate islands on the surface of these welds. So there were these 4 prototypes we looked at with different levels of manganese and silicon on the SPH 440, specifically on an 80-20 shielding gas. So not only was the base material different, but also the shielding gas was different because that was what was required by our customer in order to prove out this concept of low silicon island formation. So we looked at these 3 different prototypes, 1, 2, and 4. 3 is not shown here, but this gives you an idea of the vastly different kind of performance of these 3 different prototype wires. You look at prototype 1, and you have a continuous layer of silicate island formation on the top edge of this lap weld, and you can see the color, which is the classical rusty-looking iron oxide, which Tim had pointed out in his earlier slides. And then you go to prototype 2. The silicate island formation was not as continuous as it is in prototype 1, but it was forming on both the top edge of the lap joint as well as the bottom edge of the lap joint, but in a very discontinuous fashion. So even though it didn't form this continuous chain, but it did form silicate islands on both the top and the bottom leg. Now, prototype 4, if you look at it, performed much better than 1 and 2, and had a very nice appearance from a silicate island formation on this particular base material with this particular shielding gas, which was required by the customer. So it gave us an indication of the complexity of electrode design, which was tied to not only the procedures, not only the waveforms, but also to the base material. So then we took this prototype 4 wire and then said, now what can we do from our waveform side in order to maximize the performance of this particular wire? And as you can see here, we have 3 different waveforms: Rapid Arc LS, which is our preferred waveform for a low silicon type solution with this particular wire under these particular shielding gas combinations. and precision pulse, which is a standard, which is a little bit more of a standard pulse waveform we have in our portfolio. And you can see that the Rapid Arc and the Rapid Arc LS are close, but still Rapid Arc LS perform the best amongst this group of waveforms which we tried with the prototype 4-wire. And this is again a cross section which as automotive tier 1 customers you probably look at all the time. This is just to show that all 3 waveforms actually performed fairly well. Rapid Arc was from both from a silicon island formation as well as from a penetration standpoint performed fairly similar to the Rapid Arc LS, but we felt that the Rapid X LS gave us a slight advantage when it comes to both formation of silicate islands and just the general stability of performance of this wire on this particular base material under these shielding gas conditions. So what this definitely told us was that we have a specific alloy content which has been tailored to the base material composition for the shielding gas that was required by the customer and tied to a particular waveform, which is a Rapid XLS waveform, which gave us the best combination of both the electrode base material waveform procedure for giving the lowest silicon island performance. And this is from a real world type application, a control arm, where you can see there's almost no silicate island formation on the weld and gives a really nice, clean appearance in an actual joint, which you would typically see in the field. And with that, I'll turn it back to Tim.
All right, thanks, Badri. So I apologize. I've gotten a couple messages from colleagues that my audio may not have been the best possible during my earlier discussions. Hopefully it's a little better now and will last for the duration here. What we really just wanted to do was summarize what we talk about. We finished with some new developments, but we wanted to emphasize that there's still excellent performance available depending on the base material in particular. Excellent performance available from what we would classify as our microalloyed wires, either the Super Arc L59 or Super MIG HD products that we make and other ones that we make in various regions of the world, coupled with a Rapid X waveform or a similar waveform that provides a short arc length, narrow arc tone, and minimizes that droplet exposure, along with optimizing this torch positioning that we have discovered. We put those 3 together and we think we can get excellent performance on many base materials right now. As we continue though with new wire development, we're going to be testing this on multiple steels as Badri indicated. We hope not to have to modify that for many steels, that this becomes a sort of a standardized wire design. One of the things that we also recognize is that within the automotive industry, many of these same chassis and frame type components are going to be zinc coated. So we'll be doing testing on that with that wire formulation and waveform, the Rapid XLS, on zinc coated materials. We have already started a corrosion study with PPG. Some of the pictures that I showed, the images earlier about with paint adhesion, are samples of welds that we've are currently about to be submitted to corrosion testing. So we're going to have coating and corrosion test results in the very near term, proving hopefully that what we expect, that the life is going to be significantly extended with the new design of wire. The other question really becomes OEM specifications, whether it's automotive industry or agricultural products. Are these going to become standardized? Are they going to become specified? And what are the AWS classifications for those in the various or electrode classifications in various regions of the world? That's some of the work that will be done once this is kicked off. The launch time period, really looking for this wire waveform and the optimized performance, the whole package and wire and waveform, we expect to be late Q2 or early Q3 this year. We expect to have samples and are very close to launching, but need to finalize some of this testing and complete the corrosion testing as well. So with that, we would like to thank everyone for attending. And Beth, I'll turn it back to you and see if there are any questions that have come in from any of the people that have been on listening.
Yes, we do have a couple questions. So the first question is the ideal wires. What are the ideal wires? to work in environments with the presence of hydrogen sulfide with GMAW process. So that's the end of their question. They're asking for recommendations.
For presence of hydrogen sulfide, Badri, you're the metallurgist here.
I'll take that, Tim.
Yeah. Okay.
I'm assuming that this is I'd like to know a little bit more about the application. So maybe Elizabeth, we can communicate directly with the person who's asking that question, because typically we see hydrogen sulfide in more of an oil and gas kind of an environment. Our SuperArc L56 has been used in hydrogen sulfide environments, but we need to get a little bit more information.
Okay, I will reach back out to him, but in the meantime, I will give you another question until we get a response back. So our next question is that throughout the presentation, we have referenced RapidX waveform. What machines, power sources have that feature?
So that's a good question. I didn't go power source side of things because we're really looking at well deposit, but the RapidX waveform is available on any of our power wave machines. They do require, the RapidX waveform does require an STT module, so there are a certain number of our power waves that are compatible with the STT module. RapidX ways we achieve that low voltage operation is by combining our STT process, which is a low amperage, low spatter type of process, with our RapidArc process, which is a high speed, low spatter type process. So it is a power wave platform that we'd be looking at for really the optimized solution, along with an STT module to give us the best performance possible.
Okay. What kind of additional alloys in the filler metal help provide the improved silicate performance on these harder to weld steels?
Badri, I'll hand that to you.
So in general, I would say, silicate formation is all about trying to figure out how do you manage the oxygen in the environment and try not to form large oxides that remain on the surface of the weld. So it's I can't obviously give you exactly what the formulation is, but generally it's a combination of strong deoxidizers, microalloying elements that have an affinity for oxygen, and surface active elements that can change the surface tension of the silicate islands on the surface, so they are not able to agglomerate and form large islands.
Okay. Perfect. I do believe, hold on one second, we did get a little bit more clarification on that earlier question. So, Badri, if we could circle back around to that, if that's okay with you. So the original question is, what ideal wires to work in environments with the presence of hydrogen sulfide with GMAW process, which would you recommend? The attendee came back and said that they work at a refinery, and currently they recommend ER70S-2. They currently use ER70S-6. And there's a discrepancy between the concepts with cracking and the presence of hydrogen sulfide. Does that provide any additional information for you?
So our SuperArc L56 has been used in many similar type of applications where H2S is present. That is a ER70S-6 type product. I do not know of our L52 product, which is the 70S-2 product, being used in H2S type environments as much. We have a lot more experience with the SuperArc L56, and that would be my preferred product for this type of an application. But from a technical standpoint, I don't quite don't know why 70S would perform 70S-6. A lot more history with 70S-6, our L56, the SuperArc L56 product. H2S, I mean, typically you're looking at very small contaminant levels in your wire that could affect it. It's more of a product quality stand rather than a chemical composition difference between an S2 and an S6. I hope that answers. If not, the customer can contact me directly and we can have a conversation.
Okay, great. So this question is from Dave. Do you know how well the new prototype wire works with 9010 gas?
So we have not tested that yet. The wire was developed, as Badri showed in previous slides. The wire was really developed and designed to give us optimal performance on an 80-20 gas mixture. So that is sort of a higher hurdle or a threshold to achieve the silicate formation, because the more CO2 content we have in the gas, the more surface silicates we expect to see. Some of the additional material testing, I'm sure, will include 90-10 gas mixture testing as well, but we really just have not pursued that yet, just knowing that 90-10 gas mixture is preferable to the, yeah, you should make it better. We haven't tested that yet.
Okay. Our next question is, what kind of additional alloys in the in the filler metal help provide the improved silicate performance? Oh, sorry, and maybe I did ask you that question, or a similar question to that? Performance?
Yeah, we covered that.
Yeah.
Yeah. Let's see, I think maybe one more question, and then we might be close to time here. But there's another question regarding waveforms and the best waveform to reduce the silicate islands.
Okay. What is that best waveform?
Yeah. Mm-hmm.
So our on most of this has been RapidX has shown it's whatever we can do to give us the desired welding performance, the weld size, deposition rate, with a low voltage output, as low voltage output as possible. So RapidX has really been the desired output to use for this application, because it does maintain a shorter arc length, very narrow arc cone, and runs at a lower voltage. So that's been our preferred one. Now, when you get into maybe heavy fabrication and other applications that might require a little lower travel speed, a little higher voltage, and a broader arc, there's additional testing we can be doing. We just haven't done a tremendous amount of it. Something like our low fusion pulse would be, to me, is a very logical selection for that. It's similar to RapidX in some ways, but designed more for manual operation and heavy fabrication type of welds. So slow travel speeds, slightly higher voltages. So those would be the most likely scenario. But again, we could, depending on customer application, I think we might be able to do some experimentation with them to work on that together.
Okay. So this question, and this might be our last question here, but it's how can we reduce the silicates on the galvanized material? The parameters are 85 argon and 15 CO2. The application is a bumper.
Yeah, the galvanized material is one of those areas that we do see. Part of it has to do with arc stability. Part of it has to do with, in this case, I would look at gas mixture as being one of the first components that we would look to change. Going from an 85-15 to a 90-10 gas mixture is going to improve should improve the current operation. The wire selection, I guess, not knowing what that wire currently is that's being used, there might be an option for us to look at different wire selection. And then the process, what kind of parameters are being run on this bumper application? And speed, higher travel speed, and low voltage operation are going to be our best foot forward. So I would look again at something like a RapidX waveform to be used on a bumper application on zinc coated material. So anyway, that would be the recommendation. And actually, as it pertains to zinc coated material outside of the silicates, we will be having another webinar next week, next Wednesday, the 22nd, specifically covering the different solutions that we have for welding of zinc-coated steel. So MIG brazing, solid wire, metal cord wires, the whole gamut. We will be talking about specifically zinc-coated applications next Wednesday, not necessarily related to silicates, but really related to weld quality and productivity and what we have to offer there. If whoever the listener is on with that question, we may listen in and cover that again. But again, gas mixture, process, and selection would all be the questions I would look at. We know what the gas mixture is, but what is the wire and what type of output are they using currently would be the questions to see if we could make some improvements there.
Okay, thanks, Tim. Yes, that gentleman did send in what the wire was, but we could probably take this question offline if you wanted to reach out to him. Okay.
I'll look into it. Yeah, we'll get that afterwards, and we'll reach out.
Okay, great. Well, thank you guys for your presentation today. We are at time, and knowing that we want to keep these pretty close and tight, we want to wrap up for the day. So I want to thank both Tim and Badri for all of that excellent information. And if anyone is looking for solutions centered around our transportation, please contact either Tim or go to your local Lincoln Electric representative. Thank you, guys. Thanks, Tim and Badri. Thanks,
Beth. Appreciate everyone's time, and please contact us if you have any further questions. We appreciate all the business and look forward to seeing face-to-face in the near future.
Great. Thank you. Bye-bye.
Bye.